Hello everyone, welcome to the class. I hope you are doing good and you are enjoying learning physics with me. In the last class we were talking about gravitational field strength. We learned about how to find the gravitational field strength due to a point mass due to a ring. Today we will go ahead and we'll find gravitational field strength due to certain more objects. We will start with the first one, gravitational field strength due to a rod. Let's go ahead how it looks like. So we're going to learn gravitational field strength due to a rod. It's a uniform rod. Whenever I take any object that has to be uniform. So gravitational field strength, that means intensity also. You can use the same term as gravitational field intensity, field strength due to a rod. Now a rod, it's generally a thin rod and mass is uniformly distributed. How will it look like? Let's say this is a rod and the variables used to specify it, we are giving its mass capital M and its length as capital L. Let's say it has got mass capital M and its length is capital L. Now where are we interested to find out the gravitational field strength? That is the first important thing that we need to note down. Now you can find out the gravitational field strength anywhere, but let us take some point where symmetrically we can find out the value of gravitational field strength. Let's go and find out the first position, that is at an axial point. Let us evaluate what will be the value of gravitational field strength at an axial point. Now let's say we have any external point here. Let's call this point as point A, and suppose this is lying at a distance of small r from this end of the rod. Now as I have told you, gravitational field strength, it's a vector quantity. It has got direction and its direction is always towards the object. So the gravitational field strength at point A due to the entire rod will be towards the rod. So it will be directed towards the rod. I am showing you with this arrow sign. This is the value of gravitational field strength. Now before starting, you see this cannot be taken as a point mass. The mass is distributed all over its entire length. And since mass is uniformly distributed, so every unit length will be having same mass. Let me give the entire mass of the rod as capital M. Let us say mass capital M is the mass of the entire rod, its length is L. So how to find out the value of field strength at this point? We will start with the concept of field strength due to a point mass. So what you do, you take a point mass anywhere within the rod. Let's say you have taken here, and this is at a distance x from one end of the rod. You have taken a width. Let's say you have taken a width that is given as dx. Let me show you separately that this length is dx. Dx length is this and its mass is dm. Its mass is dm. The small particle which you have imagined within the rod, its mass is dm, its width is dx. So what I'm going to do, I'm going to show you that its mass is dm. Mass per unit length is same. So how can we give the mass dm in terms of small width dx? See how we can give the mass. First of all, we are learning the first case, that is field strength due to rod at an axial point. Field at an axial point. Why axial point? Because it is lying on the axis of the rod. Field at an axial point. And r, the distance that you can see, that is from one end of the rod. Now we have taken a small particle of mass dm at a distance of x from one end of the rod. Now x has to vary. X has to vary. As x is going to vary, you can find out the entire gravitational field strength due to the entire rod. Now you see here, if x is 0, then this part will lie here. When x equal to capital L, this part is going to lie here. What we can do, because since we are finding from point A, so can we increase this length and can we measure this length from this point A to simplify our calculation involved? You see here, when this part will lie at this end, x will be equal to small r, because we have to find for this point A, and when this part will be lying here, then x will be equal to L plus r. So we got the limits. To cover the entire rod, you have to vary x from small r to L plus r. This is what you have to do. Now you see here, let's go ahead. Let's write the small mass dm as equal to total mass, total length multiplied by width of the segment that we have taken, width of this part, that is dx, that we have taken. Now field due to this small mass, this will be how much? This will be small gravitational field we will be having, and that will be directed towards this small mass, and the distance that we have taken, that is x. So if I mark this small field as dg, because I am going to represent the gravitational field in terms of using the value g, let me use dg as the small field due to the small mass. So dg will come out to be, now using only its magnitude, that will be g dm upon x square. The value of dm can be substituted here, so we will be getting gm by L x square dx. This is the value of dg that we have obtained. Now see, gm by L, or a constant, only x is varying. Now easily we can find out the field strength due to the entire rod. You vary x, you have to cover the entire rod. You see here, when this particle will lie at this end, x initial limit will come out to be, and that will be equal to small r. And when this particle is going to lie at this end, then the value of x will be r plus capital L. So vary x from small r to L plus r, you are going to cover the entire rod. You are going to find out the value of gravitational field due to the entire rod. Let's go ahead. dg, now we got here. Can we perform integration? So on performing integration, we will be getting g is equal to integration of dg. This is equal to integration of, let's keep gm by L outside, and we will be having 1 upon x square dx. This is what we have obtained, and vary x from r to r plus L. I believe that you can clearly see till the upper end. And let's go ahead, let's write down the integration, gm by L and 1 upon x square integration. If you remember, you can perform this integration using the formula for x power n. X power n integration was 1 upon n plus 1 multiplied by x to the power n plus 1. Here we have x to the power minus 2. So 1 upon minus 2 plus 1 will give you minus 1. So you will be having one minus sign, and minus 2 plus 1 will give you minus 1. So x power minus 1, that will give you 1 by x. Limits r to r plus L. So we obtain the limits. We have a minus sign here. Whenever you have a minus sign in the definite integral portion, you can substitute the lower limit first and then subtract by substituting the value of upper limit next. So what we are going to get? We are going to get gm by L. Substitute the lower limit first, you will be getting 1 by r minus 1 upon r plus L. This is the value of g that you are going to obtain for the rod at an axial point, the value of field strength at an axial point. This will be the formula, gm by L 1 by r minus 1 upon r plus L. Hope that easily you can evaluate the value. What I want you from you all, try remembering this formula, gm by L 1 upon r minus 1 upon r plus L. This is required. And the direction of the field, the next important point. Since the entire mass is lying towards the left of this point, so the field will be directed towards left. As you can see, this is towards your left. So the field will be always directed for each point mass that we can take within the object. Each point mass will generate a field, and that field will be directed in a unique direction, and that will be towards left. So the net direction of the gravitational field will be towards the rod, and which I have already shown you here. So what I can do, I can mark g vector here showing the field is directed along this, and its formula, you all can see this, it is capital Gm by L 1 upon r minus 1 upon r plus L. Once again, a very quick recap to do the entire derivation. You take the rod, remember you cannot treat it as a point mass, so we cannot use the formula for field due to a point mass to calculate the field at any axial point. So what we are going to do, we are going to divide it into many point masses. One point mass we have taken at a distance x from this point A. Field due to this point mass will be directed here, and that field comes out to be g dm by x square. Substitute the value of dm in terms of the width dx, which I have done here. You can see here we have found the value of dm, substituted here, we are going to get this. Now go ahead, vary the value of x to cover the entire rod. So we are going to get the final formula here. Easy, simple, not too tough. Now anything, if it's required in the examination, anything is asked in an objective question, if a question comes, what is the value of field strength due to a rod at an axial point, you can directly click on this and tick on this option that this will be the value of field strength, and you can get an easy marks for this. Let's go ahead with the second location, second position actually. Where is the other position where you can find the value of field strength? One we have done at axial point. Can you think of the perpendicular bisector? That is also known as the equatorial point. Let's do the case 2, field at an equatorial point. What I'm going to do, I'm going to rub some parts and I'm going to use rest all the value as it is. Field at an equatorial point. dm will be here. What is an equatorial point? I have to show you a different diagram to understand this field at an equatorial point. Let me show you the diagram. How will it look like? Let's say this is the rod. I hope that you all can clearly understand when I'm going to draw the rod a bit lower than where I have drawn it earlier. This is the rod segment which I am going to show you in this diagram. Now we are interested to find out the field strength at an equatorial point, that is at the perpendicular bisector of the rod. Where is the perpendicular bisector lie? It will be here. So I am going to draw a perpendicular bisector, this line, and anywhere you can say that this is point A at a distance R, where you have to evaluate the value of field strength. This is the value R where you have to evaluate the value of field strength, and this length of the rod is still its capital L and its mass is still capital M. So I'm also marking its length as capital L and its mass as capital M. So how to find out the field strength at this point? Now again, this cannot be treated as a point mass. So we'll use the concept of point mass and then we will escalate that concept and we will reach how to find out the value of the field strength to the entire rod at an axial point. What do you do? Take any point mass anywhere. So we have taken a point mass here. Let's say it is lying at a distance of x from this point, from the perpendicular bisector, it is lying at a distance x, and its width is given as dx. Its width is given as dx. So easily we can say that its mass dm will be equal to m by l into dx. That already we have used the same thing. Now how will be the sense of the field strength due to this small segment that we have taken, small part that we have taken? If you join these two lines, if you join this point mass with this point A, you see it will be directed here. That means field strength will be directed here, dg. Small field strength due to this small mass dm, it will be lying here. Let's say this angle is theta. Let's say this angle is theta. So this will be the field strength that will be lying here. Now you see here, can we divide this field strength, small dg, into two components? One vertical component, one horizontal component. See what we are going to get. We are going to get one vertical component and its value will be, I am marking here, its value will be dg cos theta, and one horizontal component, that will be this will be dg sin theta. Now you see here, can you also take a similar segment at a distance x at the left hand part? We can take another segment. Again, its value of gravitational field strength will be lying in this line, along this line. It will be also having two components, dg cos theta and dg sin theta, but dg sin theta will be lying at the left end and that will cancel out this effect. So we are seeing that the horizontal component is cancelled out and only component that we are left with is the vertical component, and that is dg cos theta that you can see here. So what you have to do to find out the net gravitational field strength due to the entire rod at an equatorial point, you have to add such vertical component. So you have to add dg cos theta, you are going to get the net value of the field strength. Let's go ahead, let's do this. Let's add the gravitational field strength due to such small segment. Now the value of dg, see it will be what? Value of dg will be g dm divided by its distance from the point A. R is this, x is this. So square of this distance will be r square plus x square. Quite obvious, not too tough. R square plus x square. We got the first value of field strength. dm can be easily substituted as m by l dx. That's quite obvious. So what I'm going to do, write dg again is equal to g m by l r square plus x square. Hope that you can easily verify that I'm writing x. Sometimes I write small, but I also speak also the term so that you can easily make out gm by l r square plus x square, and here we will be having dx. We got it. You see here, this is the value of dg, but we have to integrate dg cos theta. You can see here x is the variable that we are using. X is the variable that we are using. So to cover the entire rod, x should vary from left end to right end. Now when this dm mass is lying here, the value of x, because x we are measuring from this perpendicular bisector, it will be minus L by 2, because you are going towards the left end from this line, from this origin line. So that means initial limit of x will be minus L by 2, and when this dm is lying at the extreme right end, then the value of x will be lying, that will be equal to plus L by 2. So the limits of x will be minus L by 2 to plus L by 2. This is what we are going to put in our integration. Let's go ahead. dg we got here. A very large number of particles of same mass m are kept at horizontal distances of 1 meter, 2 meter, 4 meter, 8 meter up to infinity from origin. The total gravitational potential at origin is A minus 8 gm, B minus 3 gm, C minus 4 gm, D minus 2 gm. So you all must be remembering for the formula of gravitational potential, that is given as minus gm by r. So what I'm going to do, I'm going to first write down what is the formula for potential. If we have a point mass, the potential at any distance r is given as v equals to minus gm. Let me show here that we have taken small m. So this will be minus gm by r. This is what we know, and it's a scalar quantity, so we need not to consider anything about direction. It's a scalar quantity. It will be having only magnitude. Now, as per the given instruction in the question, you see here a very large number of particles. There are many particles. They are located at 1 meter, 2 meter, 4 meter, 8 meter up to infinity from origin. So what I'm going to do, I'm going to show you how these particles are located. This is y-axis, this is the x-axis, and the particles are located here 1, then you see 2, now it will be at 4, the next particle, third particle is at 4, and the fourth particle is at 8. This is how the particles are located as per the given instruction in the question. So m here, m here, m here, m here, and the pattern continues. Now due to each particle, we need to talk about the potential at origin. Potential due to this particle, which is located at 1 meter, it will be minus gm by 1. Potential due to this particle, minus gm by 2. To do this, minus gm by 4. To do this, minus gm by 8. If I go ahead, if I write here, this will come out to be v equals to minus gm by 1 minus gm by 2 minus gm by 4 and minus up till so on. This term will be continued. Now you see here, for this is net potential at origin, V net, that is what we are interested in evaluating. If I take gm common, and if I write minus gm common, if I write 1 plus 1 by 2 plus 1 by 4, the resultant equation will turn out to be V net is equal to minus gm. You see here, this will turn out to be 1 plus 1 by 2 plus 1 by 4 and plus 1 by 8 plus and so on up till infinity. You can see that this is an this is a geometrical progression. Okay, just you take note till here and start at the other end. Okay, now you can see that this is actually a geometrical progression. 1 plus 1 by 2 plus 1 by 4 plus 1 by 8. That means the common ratio is 1 by 2. You can easily check. Now this can be easily solved. The resultant of this geometrical progression will be equal to 2, and that's why we can write the net gravitational potential at the origin will turn out to be V net is equal to minus 2 gm. This is what you are going to get, because this value in total, its value will be equal to 2. So minus 2 gm, that is what you will be getting. So let me show you the right option that is matching. That is option number D, minus 2 gm will be the right answer for this question. Before starting next question, let me just clear the board. And let's switch to the next question of the day. Question number 2. A body starts from rest at a point distance r0 from the center of the earth of mass m. So you see that body starting from at a distance r0 from the center of the earth, and the mass of earth is m and radius r, that is given as r is the radius of earth, less than r0. The velocity acquired by the body when it reaches the surface of earth will be. Option number A, gm 1 upon r minus 1 upon r0. B, 2 gm 1 minus r minus 1 upon r0. C, under root 2 gm 1 minus r minus 1 by r0. D, 2 gm under root 1 minus 1 upon r minus 1 upon r0. To solve such question, first you draw the diagram and try to understand what is happening. It says that body starts from rest at a point distance r0 from the center of the earth of mass m. So the starting point will be like this. This is earth. Let's say the body starts from here. This is the mass of earth, and this distance is given as r0. The radius of earth is given as r. This is what that has been provided. So body starts from rest. The body is at rest, that means initial kinetic energy is 0. Distance r0 from center of earth of mass m and radius r, that is what we have did. The velocity acquired by the body when it reaches the surface of the earth will be. We need to find out the velocity of the body. Let's say the mass of body is small m and mass of earth we have already noted down, that is capital M. So mass of body we have taken to be small m. This is what we have taken. Now you see here, as the body comes down, there is no external force for this earth and body system, so that means the total energy of the system will remain conserved. That is, initial kinetic energy plus potential energy will be equal to final kinetic energy plus potential energy. So let me write that total mechanical energy initial will be equal to total mechanical energy final. So for this, we need to note down that initial potential energy plus initial kinetic energy will be equal to final potential energy plus final kinetic energy. This is what we can easily write down. Initial potential energy, we know that two bodies separated at a distance, the potential is given by minus gmm upon the separation. So hence this will be minus g capital M small m upon separation, that is r0. Kinetic energy is 0 because it is at rest, so kinetic energy is 0 initially. Final potential energy, when the body reaches the surface of earth, when it reaches here finally, so its potential energy will be given as minus g mm upon r, and kinetic energy, let me write down that as half mv square. This is what we can write. This is the thing that we need to evaluate, v. So let me show you that first of all we can cancel out this m as common, small m common, that can be cancelled out. Minus gm by r0 and minus gm by r. So we can write in simple form this. Let us take this at the left hand side. So we'll get gm, and gm is here. So gm 1 upon r minus 1 upon r0 is equal to half v square. So from this equation we can easily mark that v is equal to under root of, take this 2 here, 2 gm 1 upon r minus 1 upon r0. This is what we'll be obtaining. So let me just encircle this. This is the final speed when it reaches the surface of the earth. V equals to under root 2 gm 1 upon r minus 1 upon r0. Let's check. V is equal to under root 2 gm 1 minus upon r minus 1 upon r0. This is the option number C, which matches with the right answer. So let's mark option number C as the right answer. I hope that you would understood how to solve such kind of question. You should know the formula for potential energy. should know that from conservation of mechanical energy, the total energy remains conserved if no external force does any work on the system. So no work done on the system by external force, so energy will remain conserved. That is what we have applied here. Let's switch to the next question. Next question of the class. 2 point masses of mass 4m and m respectively, separated by d distance, are revolving under mutual force of attraction. Ratio of their kinetic energies will be A 1:4, B 4:1, C 1:1, D 1:16. So we have provided two bodies of different masses. The masses are given as 4m and m. Now you must be remembering that when two star system, they actually rotate, then they rotate about their center of mass. It's like the same thing, 2 point masses of masses 4m and m. Now you see here, if I draw here, this is mass m, and let me show that separation is given as d. This is mass 4m. The center of mass is quite obvious, will be nearer to the body of heavier mass. So here you will be having the center of mass. Now let's say they are rotating, so they will be rotating like this. This will be coming down. Now in a two body system, when they rotate under the mutual force of attraction and both body rotates, I have told you in the class that angular velocity remains the same. So if this is rotating with angular velocity omega, the same this body will be also rotating with angular velocity omega. So let me write that angular velocity with which they are rotating is given as omega, and that will be common for both the body. So you can write down that this is common for both. Next thing, now you try to understand they are rotating about this body, sorry, this center of mass. Let us try to find out what is this distance of the center of mass from both the objects. So if I say, if that is given that the total distance between them is d, so what will be the separation of center of mass from each of the body? Let us take our origin here, and if we evaluate the center of mass distance, if I say this distance is x, so how we can evaluate this distance x? It's very easy for us to evaluate. For the center of mass, you see here this distance x will be given as, or this distance of center of mass, the coordinate of center of mass we are actually interested to evaluate. For that, you see here, first of all, take the first body and its distance from origin is 0. So m into 0 plus, now see, take the second body from the origin, its distance from the origin is given as 4m, and the separation is given as d, divided by total mass m plus 4m, that is equal to 5m. So this comes out to be 4 by 5d, quite obvious. That means this distance will be equal to 4 by 5d. So I am just marking that this separation that we have just evaluated, that has turned out to be 4 by 5d. Quite obvious, this separation will be d by 5. Easily we can say that this separation will be d by 5. We got the distance of the center of mass for each of the, from each of the object, from each of the point masses. Now you see here kinetic energy, they are only in revolution. Kinetic energy is given by half I omega square. This is what we know, when a body rotates, its kinetic energy is given as half I omega square. Now moment of inertia will be actually m and this distance whole square. Try to understand, m and this distance whole square, that will be the moment of inertia of this body, and m and this distance whole square, that will be moment of inertia for this body. Omega is same. So if I take the ratio of kinetic energy, now you see two bodies, 2 point masses of mass 4m and m respectively. So first we have to write down the kinetic energy of mass 4m. Separated by distance d are revolving under mutual force of attraction. Ratio of the kinetic energies will be. So we need to write down, let me keep this as m into distance whole square into omega square. Now we need to evaluate kinetic energy of 4m divided by kinetic energy of m. So half I of 4m multiplied with omega square and half I of m and multiplied with omega square. Both will be having different moment of inertia. Omega and omega square will be common and that can be cancelled out. Half and half can be also cancelled out. So you have to only take the ratio of the moment of inertia. Now you see here, this turns out to be I of 4m. We know that I is mr square. So that is what I have written, mx square. This distance of 4m, its mass is 4m and this is d by 5 whole square. So this we will be writing 4m into its distance from the center of mass. It will turn out to be d by 5 whole square, and for mass m this will be 4d by 5 whole square. This is what we can easily see that. Now you see here 4m d by 5 whole square and here m 4d by 5 whole square. This term will be cancelled out, that is 5 here and 5 here will be cancelled out. Both are in square, they will be cancelled out. And m will be cancelled out. Easily you can check that these terms will be cancelled out. You will be having 4d square divided by 16d square. So you will be having 4d square divided by 16d square. This turns out to be 1:4. Quite simple, 1:4. That means the ratio of kinetic energy will be in the ratio of 1:4. Let's check the option. Option number A, that is 1:4. That is the first option, is the right answer. Quite interesting question. We have understood how to solve such kind of question. I believe that you would have learned how to solve such kind of question from this example. Quite helpful. Let's proceed with the next question of the class. So we are having the next question, question number 4. A planet has a mass equal to 8 times the mass of Earth and density is also equal to 8 times the average density of the Earth. So we are having a different planet whose mass is 8 times the mass of Earth and density also equal to 8 times the density of the Earth. If g be the acceleration due to Earth's gravity on its surface, then acceleration due to gravity on planet's surface will be. We have to find out the acceleration due to gravity on the planet's surface. First of all, we know that g on Earth is what? That is equal to g mass of Earth, if I mark it with E, upon radius of Earth whole square. This is what we know. Mass of Earth and radius of Earth whole square. Now for planet, what we'll be having? For the acceleration due to gravity on planet, that will be equal to g mass of planet divided by radius of planet whole square. This term should actually fit for acceleration due to gravity on the planet. Now say you check the options are given in terms of acceleration due to gravity on the surface of Earth. So we need to relate what will be the acceleration due to gravity, just how much it is related with the acceleration due to gravity on the surface of Earth. Now you see here, GMP, now say mass of planet, what is that? That is given as 8 times of mass of Earth. A planet has a mass equal to 8 times the mass of Earth. So we can write that mass of planet is 8 times of mass of Earth. Now radius of planet and radius of Earth, that is not directly given, but it's given that the density is also equal to 8 times the average density of the Earth. For here you see, density, we know that density of planet will be what? It will be equal to its volume 4 by 3 pi radius of planet, if I mark rp, pi r cube into, okay, just a minute, I did density into equal to volume. Just to write mass of planet is equal to its volume 4 by 3 pi radius of planet whole cube multiplied with volume, multiplied with its density, that is rho of planet. This is what has been given to us. Now you see here, mass of planet is what? 8 times the mass of Earth. So we can write this as 8 times of mass of Earth is equal to 4 by 3 pi radius of planet whole cube, and rho of you see rho of planet, that is also 8 times the rho of Earth, 8 times the rho of Earth. And again if we simplify, we'll be having this term will be cancelled out. We will be having mass of Earth is equal to 4 by 3 pi rp whole cube, and rho e, that is rho of Earth, that is mass of Earth divided by its volume 4 by 3 pi re whole cube. This is what we know, because mass of planet is 8 times the mass of Earth and the density of planet is also 8 times density of Earth. This is what we can actually note down. So what you take note till here, I will start from the other end, take note till here. So I believe that you would have taken note of this. Now easily you can identify that radius of the planet is equal to radius of the Earth. That is what we can write. So I can write that radius of planet is equal to radius of Earth. This is what we can easily note down, because rest of term will be cancelled out. You can see m of Earth, m of F will be cancelled out. This all terms will be cancelled out. So you will be left with this. You can easily compare radius of planet will be equal to radius of Earth. Note down this one. Next thing, just put this value here. That is what we need to evaluate. If you put this value here, you will get G on planet, that is equal to G, mass of planet is 8 times of mass of Earth, divided by radius of planet whole square, that is the radius of Earth whole square. That is, you find that it will be 8 times of GME by RE whole square. GME by RE whole square, that is equal to 8G. Right option 8G, we need to mark. You see here 8G is option number C. So this will be the right answer. This is how we can evaluate such questions. Now, I believe that you would have understood how to apply the formula for extended to gravity while evaluating it for different planets. The formula will be same that we are using for Earth, only thing that some things we are changing when we need to find the relation with the extended to gravity on the surface of Earth. Let's go to the next question. A particle of mass m is projected upwards with velocity v equals to ve by 2, and v is the escape velocity. At highest point, the potential energy of the particle is, we need to find out what is the potential energy of the particle at the highest point. A minus gmm by 2r, b minus gmm by 4r, c minus 3 by 4 gmm by r, d minus 2 by 3 gmm by r. So here you have to find out at highest point the potential energy of the particle is. What is the potential energy of the particle at the highest point? First of all, let me actually show you the situation, what is happening. This is our, let's say, Earth or anything. Particle of mass m is projected upwards with velocity v by 2. From here, a particle is projected with a velocity given by ve by 2. This is what has been provided. Now, for escape velocity, you must be knowing that it is equal to, if the kinetic energy obtained due to escape velocity, that is equal to half m ve whole square, and that is equal to the potential energy on the surface of Earth. So that will be equal to, and that only magnitude, I am not adding a negative. For magnitude I am writing gmm by r. This is what you should know. M and m will be cancelled out. We all know that v whole square will be equal to 2 gm by r, and I have also discussed the same formula in the class also. So for v, we have got this relation. We have to find out the potential energy at the highest point. At the highest point, when it reaches the kinetic energy will be 0. Again, no external agent is doing any work on this Earth and particle system. The total mechanical energy of the system will remain conserved. So let me write down total mechanical energy remains conserved. So total mechanical energy initial is equal to total mechanical energy final at the topmost point. This is what we will be evaluating for total mechanical energy final. Now for here you see total mechanical energy initial, it will be half m ve by 2 whole square, that is the kinetic energy initial, plus potential energy, that will be minus g mm by r. This is what we know. At the highest point, we need to find out the potential energy. So let me write down UF, that is the potential energy at the highest point, plus kinetic energy, that will be 0. I have not written here kinetic energy, potential energy separately. You can easily see that this is kinetic energy, this is potential energy, this is potential energy, this is kinetic energy. Now, if we evaluate this, already I have disclosed the formula for V in terms of Gm by R. You see, V is equal to, V whole square is equal to 2 Gm by R. This is what we should actually put. So for here you see 1 by 2 and this 2 square will become 1 by 8, 1 by 2 into 2 into 4, 8 into m, and VE whole square. V whole square, you can easily see that that's equal to 2 Gm by R. So let me put that equal to 2 Gm by R minus Gmm by R is equal to final potential energy. For here you see this will be equal to 4 times it will go 1 minus 1 by 4, you will be getting 3 by 4. So, this will come out to be minus 3 by 4 GMM by R is equal to final potential energy, minus 3 by 4 GMM by R. Let us check with the required option. If you see 1 is incorrect, 2 incorrect, third one matches. So, option number C, minus 3 by 4 GMM by R is the right answer for this example. Now, let us proceed with the next one. I hope that we understood for how to use escape velocity formula in such questions. And such questions practice will be very much helpful for you also, that you can increase your accuracy and speed so that you can